Hello, and welcome to this lesson on geometric transformations. This is the start of a new unit all about geometric transformations. This very first lesson here has a lot of vocabulary. This is kind of going to give us the vocabulary we need for the next bunch of lessons. And you can actually see some of the vocabulary words down here that we're going to be talking about. So the central question says, how do I identify rotations, reflections, translations, and dilations? So that's really our goal in this lesson is if they gave me a picture, I want to say, ooh, that guy's a dilation, that one's a rotation, that one's reflection, and we're going to talk about how we can differentiate them. Did you know that video games, well, used to use transformations all the time? In the first Mario, so if I scroll down just a little bit to get that thing out of the way, there we go. So if this very first Mario is the pre-image, another one of our vocabulary words, each other Mario represents a transformation done. So this is what they would do. Like they would have one picture, and then to make Mario move, they would literally just take this guy and move it over here. That's a translation. And if Mario was walking downhill, now they didn't actually rotate him much, but if he was walking downhill, they would just do a little rotate. If he was facing to the right and then he'd turn around and face the left, they would literally just take the picture and flip it over. Now he's facing to the left. And let's say he ate like one of the big mushrooms. This is one way they could have done a dilation. They could have made him bigger, is just dilate the exact same picture. These are all just copied and pasted and then moved, turned, flipped over, made bigger. But that's what a transformation really is. It's just taking an image and changing it. So we're going to start into a little bit of vocabulary here. There's like 7, 8 vocab words, so it's going to take a little while. But once we get through this, there's no vocabulary, I don't think, hardly the rest of the lesson. So we'll kind of get it all out of the way right now. So rotation. A rotation is when you take a two-dimensional figure and it's rotated around a point. So we'll call that a turn. So if I have, I'm trying to think of an image to draw here. All right, so I have this. If I take this, and I'm going to try to rotate it around this point right here, that 90-degree corner. So, I mean, it's kind of getting a little bigger and smaller, but that would be a rotate. It's kind of rotating around a point. It's turning. It's spinning. These are lots of synonyms for rotation, but it's a rotate. It's a turn. Okay? A reflection. A reflection is when you take a two-dimensional figure and it's reflected across a line. Now, I can't use the notability magic to do this, so I just have to draw this one out. So if I had a figure, let's go with that same right triangle, and I wanted to reflect it across, say, the y-axis. The y-axis is a line that looks like this. So for me to reflect this, it would basically be a mirror image, but on the other side of the line. So this would reflect over. It's flipped over this line. That's why it's sometimes called a flip. You can flip across the y-axis. You can flip across the x-axis. You can even flip across other lines like x equals 1 and y equals 10 and even weird lines like y equals x. Those are all possible reflections, but it is just a flipping over the line. A translation is when you take a two-dimensional figure, or when a 2D figure is moved from one place to another, sometimes called a slide. So if I take that same right triangle, there you go. I want to make it a little bit longer. Copy. Paste. There we go. I wanted to match up, so there it is, right? So now I'm going to take the one, I'm just going to go whoop. That is a translation. My translation is just, I've just moved it. I could move it up here. That's still a translation. It doesn't have to be just left, right, and up, down. You can move it diagonally, or you can move it like up some and to the right some. That's okay. But you notice how they look exactly the same. They're the same size. They're the same shape. In fact, all of them, on this page, same size and shape. Well, should be. My drawing's a little ugly there, but same size and same shape. If I would take this guy, let's give it a shot. Copy. Paste. Move them up here. All right, now I'm going to try that. Oh, man. I don't think I can rotate because this can rotate all of them. Darn. So let's imagine we rotated it. There. We rotated around that point. So all of these are the same size and shape. Same size and shape. Same size and shape. We're going to learn that has a couple special names that we can use. Now, the last of this type of transformation, a dilation, is different. This is the only one that doesn't keep the same size and shape. So it's a rule that moves points in a plane a specific distance, determined by the scale factor r from center point O. Now, that's a very confusing definition of it. It's a zoom. So if I take my triangle, boom, 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 and I take it, and I'm using 2 fingers, and I'm going to pinch to zoom, boom, that is a dilation. I just made it bigger. I made it bigger again. Now I can zoom in, I can zoom out. Notice how the shape, it's getting bigger, but it's getting proportionally bigger. If I zoom in, the length this way and the height this way are both getting bigger. Like it looks like the exact same shape. It's not being distorted. It's not being like stretched out in one direction. That's what a dilation will do for us. You may have heard the word dilation like when you go to, say, the eye doctor and they put the little drops in your eyes and it hurts your eyes. Well, because what that's doing is it's taking on your eyeball, your pupil, the part you see from the black dot in the middle of your eye, it's taking that, and normally it's pretty small and the doctor has his light shining in it, but the doctor wants to see the back of your eyeball, so he takes those things. Oh man, I'm trying to zoom. There we go. And when he puts the dots in, it makes that black part of your eye really big, so he can actually look further into your eyeball, the back of your eyeball, and see stuff. So that's what a dilation is. It's making something bigger or smaller. It's changing the size. All right, so those are the 4 types of transformations. These are actually the same 4 types we have up here. Translation, rotation, reflection, dilation. Those are the only 4 types of transformations we're going to talk about. Now there's a few other words that kind of go along with. Things like pre-image. Now you could probably take a guess before even looking at the definition. Pre means like before. Well, the pre-image is the old figure, the original, before the transformation took place. So before. Pre. Those things kind of go together, right? So the pre-image is the original. It's what happened before the transformation took place. The image then would be the new one, the new picture after the transformation. And you see these kind of like A, B, C, D, A line, B line. That's how most of the figures are labeled. So if I had a triangle, I'll use that same ugly triangle, I would call it A, B, C. Now, if I took that ugly triangle and I copy, and I'm going to do a transformation. So I'm going to do a translation. So there's the original. And when I translate it down, let's say 8 units or whatever, now it becomes A prime, B prime, C prime. So yeah, that's A prime. That's what we're saying. A prime, B prime, C prime, D prime. That's the name of that little line. That's how it's pronounced. Okay, so it's easy to tell which of these would come first. The one without the primes is the original. And these little prime lines tell you how many transformations took place. If I did another transformation, I could have a second boom, boom, boom. So it'd be like a B double prime, C double prime. So that would be a second type of transformation. Okay, and if this seems a little weird right now, it's okay. We'll make sense of it all over the next bunch of lessons. I think these are the last 2 vocab words, and they're fairly important throughout the course of the unit. So congruent. Congruent is a math word that means something like they're almost equal, but we can't say equal. Like two triangles aren't equal to each other, but they're like identical. They're identical twin triangles. So it's two objects that are similar if they have the same shape and size. And similar is not really the best word to use here, because the next word is similar figures. So this should be probably congruent. Two objects are congruent if they have the same shape and size. Congruent figures are the result of rigid transformations, and that's kind of a hidden vocab word in here as well. A rigid transformation. Rigid. That word means hard, not flexible, not movable. So a rigid transformation is any transformation where the preimage and the image are like twinsies, where they're the same exact size, shape, everything. Okay, imagine you drew a triangle on a piece of wood. You can take that piece of wood and you can flip it and you can spin it and you can turn it, but that triangle is always exact same size and shape. That's because wood is rigid. It doesn't bend. It doesn't flex. It doesn't get bigger and smaller. Okay, so rigid means hard, not changing, firm. Now, similar figures are two objects are similar if they have the same shape but a different size. Similar figures are the result of a non-rigid transformation. Again, non-rigid would be because, well, it can get bigger and smaller. They're the same shape but a different size. And the best example of a similar figure that I can draw for you is a dilation. If I copy this guy and I paste him over here, and then I'm just gonna make him bigger, whoomp, that's a dilation. That is non-rigid. You can't do this with a piece of wood. You can't just take something smaller and magically make it bigger by stretching the wood. Wood doesn't do that. It's because it's non-rigid. But these guys are the exact same shape, but a different size. See? Same shape, different size. Those are similar figures. Okay. So now that we've got the vocabulary out of the way, let's start talking about some of these transformations. So, describe the given transformations. Use these words: rotation, reflection, translation or dilation, rigid or non-rigid, similar or congruent. So here we have our pre-image, image A, B, and C. And so what we're going to need to do is we need to figure out, like, from the pre-image to image A, what happened here? What type of transformation is this? Now, in most of these, there's like 3 different levels of how good your response is. So for example, from here to here, this was not turned, it was not flipped over, it looks like it was just moved over here. That is a translation. That's a good answer. It's not a great answer. We can do better. Now, we'll do better in a second first. Let's just get the good answer for each of these. Image B, from this thing here to this thing here, because again, pre-image is the original. What happened from this to this? I mean, did I flip it this way? No, flipping I don't think would work. This is a rotation. This spun probably around the origin. So this would be a rotation. And then the last one, letter C. What's going on here? What type of transformation is this? Well, it looks like it's been flipped over this line. Like this is a mirror image of each other. That is a reflection. Okay, now, each of these is a good answer. That's the basic answer that we want, okay? But we would like to do better than a basic answer. We like a proficient answer or an advanced answer. So let's add more details, and we can do that right now. So this translation here, well, how is it translating? Did it translate up, down, left, right? How many units? Well, we could figure this out. Now, one of the biggest mistakes students make is I see a lot of students say, oh, this was a translation up to right 3. They're going from here, 1, 2, 1, 2, 3. The problem with that, though, is that doesn't actually work. If I would trace this, and I take this whole thing, and I go up 2, boom, boom, over 3, boom, boom, boom. That's not in the right place. This should be over here. So when you're like translating, when you're moving, or when you're shifting the figure, you got to go from like corresponding parts. So like this corner here would need to go the whole way to that corner there. It's the same part, but on the other picture. Well, how is that translated? That's translated still up 2. I'll take that. But now instead of being to the right 3, it's the right 1, 2, 3, 4, 5. That is now a pretty good answer. So we have image A is a translation up to right 5. There's actually one more level of answer we could do to this to make it even better. A lot of times you'll see translations given as like a mathematical rule. So here's how this is going to look, and I'm just going to show you this one, and then we'll talk about it. So x comma y goes to, the x value goes up by 5, the y value goes up by 2. Now, you might see some connections between this thing and this thing. And how did I get it? Well, when I was here, and we went to the right 5, 1, 2, 3, 4, 5, what is happening is our x value, this x value right here is -2. But my x value is getting bigger, 5 units. Now my x value is +3. So my x value went up by 5 units. That moves me to the right 5. My y value went up by 2. This has a y value of 1. This has a y value of 3. It went up 2. So this is the best possible answer for this. I have a translation up to right 5 using the rule. This is the rule, the mathematical rule that tells us how to translate this. Okay, this is a lot of information for one problem, but this will become more familiar as you do it. Rotation. Let's change color here. Let's go with red. All right, so rotation. Image B. What's happening here? Well, my rotation, I can add a couple things. I need to add how much did it rotate? Did it rotate 90 degrees, 180 degrees? Which direction did it rotate? Clockwise, counterclockwise? And also, where's the center of rotation? Okay, all of those things take our answer from being an okay answer, a basic answer, to being a great, awesome answer. And that's what we're going for. Okay, so this rotation is down here. Now, I said that the possible choices for a rotation are either usually 90 degrees or 180 degrees. They're not going to have weird like 27 degrees because you're not going to have a protractor to use anyways. You're going to have to kind of just go by what it looks like by the image. Okay, that was pretty ugly, but it works. So a 90-degree rotation is a quarter turn. So I'm going to put my thumb here, and my other finger here, and I'm going to kind of spin it 90 degrees to show you. I'm trying to keep everything the same size and shape if possible. There. That's pretty darn close to how it was. So that is a 90-degree rotation. It basically turns something on its side. Or if it's on its side, it turns it up. This is not a 90-degree rotation. Like look at it. This is facing up, this is facing down. Well, that would be more of a half spin. That is a 180-degree rotation. So this rotation is rotation 180 degrees. That spins it upside down. Now, did we spin clockwise, the way a clock goes, or counterclockwise? Well, in this case, 180, it doesn't matter because 180 flips it upside down, or spins it upside down, so 180 this way is the same as 180 this way. You don't actually need to tell us that if it's a 180-degree spin. But the other thing we need is the center of rotation, because where are we rotating around? Like here, I pretend I rotated around this point right there. Well, you see it's not exactly lined up. I could have also rotated around, say, this point here. I mean, I could take this and go rump and rotate around that point. I could have rotated around that point right there. But one of the most common places you're going to rotate around is actually the origin. So here's what I'm going to try to do. Let me put him back to normal. Now I'm going to make a big circle here. So what I'm going to try to do, it looks like my triangle is a little smaller than it was before. There you go. So now what I'm going to do is I'm going to put my thumb right here, right at the center of rotation. And then I'm going to rotate and I'm going to show what happens. And I encourage you, if you're using an iPad and Notability, to try this as well. Actually, so let's see if I'm trying to get my hands situated right. All right, so here's one finger at the origin. So you see how it's rotating around that, and I know I'm trying to get it making a little bigger and smaller and stuff. So it's rotating around that point. That is what happened. So our rotation was a rotation of 180 degrees about the origin. Now we have an awesome answer. I have how much it rotated. We didn't really need the direction of rotation, clockwise or counterclockwise, but we also have where the center of rotation was. All right, reflection. This one's a bit quicker. So, what's going on with this reflection? Well, the reflection is always across a line. So what is the line? Where is the mirror image line? I encourage you to try to draw it. Like for me, I'm thinking it's right here. Like these two things are mirror images across from each other from this line. Well, what's the name of this line? That's the line. Well, that line actually has two names. We could say that's the line y equals 0. But more likely that has a better name. That's reflection across the x-axis. Which the x-axis is this line, y equals 0, but most people just call it across the x-axis. So that's all we have to say here. Reflection across the x-axis. Boom. That one's done. Okay. So we have good, better, best. So there's 3 different levels of answers. Good, better, best. Good, better, best. Reflection, it's just good and best. There's no really better. Okay, so we're going to pick up the pace a little bit here, just because now that we've seen it, it's going to be a little bit easier. So image A. Well, first off, let's dissect this picture. Oh, and we never said rigid, similar, congruent, all that stuff. So let's do that quick. I forgot. My bad. My bad. So image A, from here to here, this is a rigid transformation. You see how the same size, same shape, they're like twinsies. That's rigid. And they are also congruent. Congruent means like they're equal, they're identical, they're the same. In fact, all three of these are rigid, congruent transformations. Because all three of them are the exact same size and shape. All right, now we can move on. So, image A. So, pre-image is this. This is my pre-image, this big guy up here. Image A is then this little trapezoid down here. So that is a dilation. I know, because it's the only type of transformation that changes the size of a figure. That's kind of a zoom. We zoomed in or out. It made smaller. Image B. From pre-image to image B looks like a reflection. It looks like it's been reflected across this line right here. Like they look like mirror images of each other. Image C. From this pre-image to image C looks like it just slid down. Well, that is a translation. Okay, those are my good answers. Let's get better answers. We'll keep blue. So dilation. How did it dilate? Well, we need two things for our dilation to make it the best answer. We need to know the scale factor. Did it get bigger, smaller? How much bigger? How much smaller? Is it 2 times bigger? Half as big? Stuff like that. And the center of dilation. So here, my new image, image A, is smaller. Ooh, how much smaller? It used to be 1, 2, 3, 4, 5, 6, 7. It used to be 8 units tall. That's how tall the original guy is. It's 8 units tall. And now he is 1, 2, 3, 4. He's only 4 units tall. So he is half the size of the original. So it's a dilation with scale factor R equals 1/2. It is half the size of the original. Each length is half the size. So this length here was half the size of the original. This one here is half the size of the original. This one is half of that. This side is half of that side. Each side is half of what it was before. Okay, that's a good answer. So we had okay, we have better. Now let's get best. The thing we're missing now is the center of the dilation. Where did we dilate from? Because you're allowed to dilate from pretty much anywhere. Oopsie. That's not too bad for hand-drawn. All right, so for example, I could take this. I could dilate from this corner right up here. There we go. I could dilate from this corner over here. I could dilate from this corner or this corner. I could dilate from the origin. So where did we actually dilate from? Where did it get bigger and smaller? Like, where did it zoom into? Well, it looked like it zoomed into this corner right here. Check this out. Yeah, that's where it is. So the center of dilation is this corner, is this point. So we need to say that. So we dilated with a scale factor of r equals 1/2. R is like the variable we use for scale factor. About, let's see, what is that point? Since it doesn't have a name, I just have to give it the coordinates. That's -1, 1. Okay, good, better, best. Now we have all of it. It's a dilation with a scale factor of 1/2 about the point -1, 1. That is the best possible answer. Now anybody in the entire world could recreate this exact dilation. Letter B. Here, if we just said reflection, well, people can't recreate that exactly because they don't know reflection where. Well, we can fix that. So let's say it's reflection about what? Well, draw your line that represents the mirror image. So I'm thinking it's right here. This is our y-axis. We are reflecting across the y-axis. Notice that 2 units here, 2 units there, 1 unit, 1 unit. Like, it's the exact same distance on each side. So that's a reflection across the y-axis. That's the best possible answer for that problem. We just need to say, where is it reflecting across? Now anybody can say, oh, okay, so I take this and I reflect across the y-axis, and that's how they get image B. Okay, letter C. So, oopsie, I'm trying to delete. Thank you. So from pre-image to image C, we said it's a translation. We said it's basically just moving down there. Okay, how? How far? Which direction? Well, it looks like it's going, well, I would definitely say down, but it also looks like it moved a little bit to the left. Okay, we're getting better, translating down to the left. Okay, how much down? How much to the left? Let's add some detail. Well, count the boxes. Down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Down 11 units. And left how far? So if we went straight down 11, we need to go left 1 unit. Now this is a pretty good description. Translation down 11, left 1. But we can make it even better using the rule x, y. So what happens to our x value? And when we went left 1, our x value would go down by 1, right? This has -1, and now the x value is -2. It got smaller by 1. When we went down 11, what's happening to our y value? In the y, if you think of your numbers on the y-axis here, you went from +1 to -10. You went down 11 units. Now we have the best description. This is a translation down 11, left 1, using the rule x, y translates to x goes down by 1 and y goes down by 11. Now anybody in the entire world could recreate that exact same translation. All right, so now you've had a couple problems of practice with working through this together. I would like you to try one. Okay, so you're going to pause the video, and just to make sure we're clear of this, the pre-image is this little one right here, pre-image. Image C is this big guy hiding in the background. Okay, so you got A, B, C is the big one, and there's your pre-image. Okay, so you're going to pause the video. You're going to try to give not just the good, not just the better. Try to give the best answer you can for each of them. And if that for now is only just the good answer, I'm okay with that. I'm not pleased, but I'm okay. The more you can give, the better your answer will be. Okay, so go ahead and pause the video. When you're ready to continue, hit play, and we'll go through it together. All right, so let's do it. So image A, that is a translation. Translation how? Well, I'm seeing it's a translation down. I'm going to say left, then down. Left and down. Okay, left how much and down how much? Let's count the boxes. I'm going to go from this point here to this point here. So left 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Left 11, down 2. See, I can see, I just counted that in my head. 1, 2. Okay, so we're going left 11, down 2. That would be the rule, x comma y. My x value went smaller by 11. My y value gets smaller by 2. That is the perfect description of this transformation. Now, if you had translation and left 11, down 2, that's still pretty good. But see if you can make the connection, make the jump to get this rule as well. That's where it becomes a great answer. All right, pre-image to image B. So I'm going from this thing here to this thing here. Now, I don't know that it's definitely not a translation. It's not a dilation. This is either a reflection or a rotation. So let's see. If I would imagine, okay, maybe I'm imagining it's reflecting across this line right here, the x-axis. I'm seeing some problems, like here. This line is flat on the top. If this would flip up and down, then if this would be flat here, it would be flat right here. But it's not. So this is not a reflection. This is not a mirror image of each other. Oopsie. Got a little excited. This is not a mirror image of each other across this line. So instead of being a reflection, this must be a rotation. Okay, rotation. How? How many degrees? Which direction? Where's the center of rotation? So this is a rotation of 90 degrees clockwise. We can just substitute CW for clockwise, or you can write out the whole thing. If I was going to say counterclockwise, we'd use CCW, but a rotation 90 degrees clockwise, that already is a pretty good description. If I can trace this, okay, 90 degrees would be a quarter turn. So that's a 90-degree rotation. Maybe not quite 90. There, that's a 90-degree rotation. And then about where? Like, did we rotate around this point, or this point, or this point, or we rotated around the origin. So this rotation, if I can go back to the original, a little smaller. So I'm going to make this big, and now I'm going to put one finger here at the origin and the other finger here at this corner, and I'm going to try to rotate it to there. So here to here. So that was a 90-degree clockwise rotation. So this is the way a clock spins. Clock spins like this. Clockwise rotation about the origin. All right. And let's use green for letter C. Letter C. Let's see, from pre-image to image C. Image C is this big dude here. That's image C. So what's going on? Well, that's a dilation, because it's not the same size it was before. Dilation of what? Width scale factor R equals, well, how much bigger is it? Well, we have to count boxes to figure this out. Like here, this is 1, 2, 3, 4. This was originally 4 units big. How big is it now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It went from 4 to 12. How much bigger is that? And we're not going to say it's 8 bigger, because the dilation is multiplicative. It is a times. How many times bigger is it? And now you might have the idea, oh, it's 3 times bigger. 4 times 3 is 12. Each thing is 3 times bigger. My new shape is 3 times bigger than the old shape. Scale factor is 3. How many times bigger is it? Okay, we've got a good, we've got a better. The last thing we need is a best. Where is the center of this dilation? Where did we dilate from? Like if I would redraw my original here. Okay, where are we dilating from? Where is the center? Where is everything zooming in and out from? Right here. If I would take, and I'm going to keep one finger here, and I'm going to start dragging the other points. Do you see how that one corner doesn't, oh, he can't get any bigger. I have to do it in a couple stages. So that's twice as big. And then if I go again, there we go. Okay, so that was 3 times as big. But I kept my finger here. That was the center of the dilation. If I shrink a dink, I have to do it in 2 stages just from the program itself. Okay, so we're dilating about that point. Now that is the point 9, 9. I know because this grid only goes up to 10, so 9 this way, 9 this way. So it's dilating around that point. Okay, so that takes a little bit of time to do right. But man, will this pay off in the long run. Okay, last of this type, and then we get to some easier little wordy problems. We're going to fly through them. So if you could pause the video, describe each of these transformations to the best of your ability, and then we will go from there. All right, image A. So first off, the pre-image, you had to find that one. I didn't tell you this time. The pre-image is here, so this is the original. So image A, that is a reflection, and is reflecting across the y-axis. It is reflecting across this line right here. I'm counting, there's 3 boxes here, 3 boxes there. It's the same distance on both sides. That is your mirror image line. And that one is done. Image B, that one up there. Well, they're facing the same way, like they look identical, it's just over here. So that's a translation. And it definitely went up and to the left. Up how far? Pick a corner. I'm gonna pick this corner to there. You got to go from corresponding parts. So up how far? Up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Up 10. And left 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now we have a better answer. Good, better, best. Using the rule x comma y, okay, what's happening to your x value, your sideways direction? Well, that x value is going to get smaller from +3 to -8. It went down by 11. The x direction is left and right. The y went up by 10. Up and down is your y. Up is positive. You're getting bigger and bigger and bigger going up. That is my best answer. And lastly, letter C. From this thing to that thing. Well, it is not a reflection. It's not a mirror image of each other. It's not a translation like we just did because this one seems to be turned or something. It's not a dilation because it doesn't appear any bigger or smaller. This is definitely a rotation, which for a lot of students is the hardest of them. Okay, rotation, how? Well, it's a rotation of 90 degrees. And how do I know that? Well, because it's not just rotated upside down. It's not spun upside down. Like, see this point here? It's not facing up. It's facing to the right. So that's a rotation of 90 degrees. Which way? Well, this might take a little bit of brain power here. So I'm imagining this. It went like that. Like that's kind of what I'm imagining in my head. So that's 90 degrees. I spun this way. That is counterclockwise. That's not the way a clock spins. Clock hands don't spin this way. They spin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Not 6, 5, 4, 3, 2, 1. So rotation, 90 degrees, counterclockwise. Better answer. About what? Where's the center of this dilation? I'm sorry, the center of this rotation. Well, if it's not one of these four corners, one of the corners of the object, it's probably the origin. And I can check it by doing a little notability magic here. Let me turn him back. Trying to get him at least mostly lined up. All right. So now one finger on the origin, one finger on, oh man, one finger on this corner, and aha, it was the origin. Okay. So those are your best answers for each of these. And hopefully this is getting easier as you go. Okay, applications. An artist sculpts a model of a virus that is 1,000 times the size of a normal virus. What type of transformation does this represent, and how do you know? Well, this would definitely be a dilation. And how do I know? Because they're not the same size. A dilation makes things bigger and smaller. Objects are not the same size. Now, while I'm thinking about this, I'll let you do this and then pause if you need to, but we forgot to go up and, with all those other problems, tell whether the shapes were similar, congruent, rigid, or non-rigid. So let's do that quick. Okay, so we're gonna shorthand, we're gonna fly through. So this one, so from pre-image to image B, that is a rigid transformation, and it is congruent. It's rigid because it's exactly the same. It's like it was made from a piece of wood. It's exactly the same. It's just been flipped over. Image C is rigid and congruent. It's made from a piece of wood. They're exactly the same. They're identical. Image A is not rigid, but it is similar. Similar is the same shape, but a different size. Okay, so anything that is identical was a rigid transformation. So that was rigid and congruent. That one's rigid and congruent. And my big dude here, well, that is a non-rigid. Should probably use capital letters for everything, huh? Not rigid. It is similar. Similar is the same shape, different size. Congruent is they're twinsies. They're identical. All of these are rigid congruent because they're all exactly identical to this, just spun, flipped a little bit, but look, same shape, same size, same shape, same size. So rigid, congruent, rigid, congruent, rigid, congruent. The only thing that makes something not a rigid transformation for us is, so far, the dilation. Okay, now I feel better. I missed those. My bad if you were doing them and then I wasn't talking about them. Hopefully we're all good now. Letter B. A car is at a red light. When the light turns green, the car makes a right-hand turn. Would this be a rotation, reflection, translation, or dilation? Well, if you need to, you can draw a picture. So car is sitting at a red light. Here's my beautiful car. When the light turns green, the car makes a right-hand turn. He goes like that. Well, what kind of transformation is that? That would be a rotation, because I turned, or the car turned around the corner. It was facing up and down. Now it's facing sideways. So that would be a rotation. It turned around the corner. No, I think that's a good enough description of why it's a why it's a rotation, because it turned around the corner. Rotations are turns. There. Turn, turn. Letter C. James traces the shape of a dragon on a piece of cardboard. If James moved this cardboard in any direction, including turning, flipping the paper over, blah, 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 would this be a rigid transformation? Why or why not? Go ahead and pause the video, think about it. When you're ready to continue, hit play, and we'll go through it together. Okay, so this would be a rigid transformation. I'll put transformations, because if he did it on a piece of cardboard, unless he takes that cardboard and crumples it up, the size and shape of that dragon that he drew is not going to change. Okay, piece of cardboard is fairly rigid. It is a rigid transformation. So if he takes it and he slides it over, it's still a dragon. Wait. There's my beautiful dragon. Don't make fun of my dragon until you see it. Oh, man. Arm, leg, tail, wings. Beautiful dragon, and it shoots fire and everything. All right, so if he takes this and it's on his piece of cardboard. Here, let me draw his piece of cardboard too. Boom, 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 boom. Yeah, there's his piece of cardboard. Now he takes this and he hands it to a friend and he slides it over. It's still the same dragon. It didn't get bigger or smaller. If he takes it and he turns it over, it's still the same dragon. It didn't get bigger or smaller. If he takes it, and I can't show a flipping, but if he takes the cardboard and he flips it over, it would still be exactly the same. It's just flipped over, and now you can't see the dragon because it's on the back side of the cardboard. But it's still there. It's just flipped over. Okay, those are all rigid transformations. He can't make the cardboard bigger and smaller, and the dragon bigger and smaller with it. Letter D. I think this is almost the last question. It says, Pat constructed a triangle out of popsicle sticks. He then made a new triangle that is similar, but not congruent to the original triangle. What type of transformation did Pat have to do, and why? Go ahead and pause the video, draw a picture if you need to. When you're ready to continue, hit play, and we'll go through it together. Okay, so if he made a triangle out of popsicle sticks, and then made a new one that is similar but not congruent. So if it's not congruent, it means it's not exactly the same. Well, if it's similar and not exactly the same, it means you had to do a dilation. Because dilation is the only transformation we've learned about that makes similar figures that are not congruent. All the other transformations are congruent. A rotation makes congruent figures, rotation, reflection, all of them make congruent, except for the dilation. Letter E. The pre-image of triangle ABC has an area of 9 feet. Okay, so this dude has an area of 9 feet. I'm going to label that. Sounds like it might be important. 9 feet squared. The image is then flipped across the x-axis, then rotated 45 degrees. What is the area of the image A prime, B prime, C prime? So it has kind of a little sort of picture drawn here for us and stuff. So what is the area of this? Now, this is a work smart, not hard question. Because we know if you take an image and you flip it over the x-axis, for example, and actually I'm pretty sure this should be the y-axis, because you're flipping across this line here, the y-axis. But if you flipped it over, did you change the size of the triangle? No, a flipping is a rigid transformation. It makes congruent figures. So the area would be 100% the same. They're still twinsies. If you then took that triangle that you flipped over and you rotated it 45 degrees, did you change the size or shape? Well, no. So this would still have an area of 9 feet squared because these are both rigid transformations. So this area is exactly the same as that area. We didn't get bigger or smaller. We did not do a dilation. So the areas are the same. All right. Letter F. Jose is a cartoonist drawing an apple. Between two frames of a cartoon, the size and the shape of the apple don't change, but how it looks on the page is different. What transformations could have been done to the apple? Pause the video, maybe draw pictures if you need to. Do the problem. When you're ready to continue, hit play, and we'll go through it together. So if the size and shape don't change, that means it's not a dilation. Dilation, the size would change. So it could be a translation, slide. It could be a rotation, a spin. It could be a reflection, a flip. It could be one of those three. And summary. What is the difference between rigid transformations like rotation, reflection, translation, and a non-rigid transformation like a dilation? Like, what's the difference between them? What do you think? Well, rigid transformations, the size and shape of the object stays the same. They're I keep using the word twinsies. They're twins. They're exactly the same. They're identical. Where a non-rigid transformation, your new object is bigger or smaller than the original. And this has been our lesson on geometric transformations. Thank you so much for watching. Until next time, toodles.